of the most interesting intellectual endeavors you could embark on at our current time. It is right at the intersection of AI and natural language processing or machine learning. And so when we think about what are sort of the most interesting manifestations of our human intelligence, I think language comes up at the top for most in most answers. It is very inextricably linked to thought and also information, and we're in an information age, so natural language processing is an immensely useful piece of technology. At the same time, deep learning is similar in the sense that it is very broadly applicable. You can do speech recognition with deep learning, you can do image classification, and you can do a lot of different tasks inside natural language processing. So deep learning is also a very, very interesting tool for you to have going forward in your lives. And so basically we're combining these two, so it will both be interesting from an academic and intellectual perspective as well as for industry. There are a lot of companies out there right now who are trying very hard to hire people with deep learning skills, so I think hopefully this will help you both if you decide to work in an academic setting or in an industry setting. So basically, by the end of the lecture, you'll be able to build an algorithm that can kind of do what you can see here, which is it can interpret a sentence like, the first 15 minutes were dry, but by the end, I really enjoyed the lecture. And so the algorithm here learned what the grammatical structure of that sentence should be, and it assigned a label, which in this case happens to be a sentiment label, to every phrase of that sentence. And we'll basically give you an introduction of why the tree looks the way it does and why it assigns these positive and negative labels. So what's kind of amazing here is we did not have to eventually say that you have here a so-called contrastive conjunction named but really we just had to give it a lot of examples, and it was able to learn that really you can say the first part is negative, and the first 15 minutes, that is a neutral phrase, and then once you say they were dry, it becomes negative, and then you have a contrastive conjunction, which usually means that what comes afterwards matters more in the overall interpretation of the sentence. None of that we had to explicitly tell the algorithm, but it will be able to pick it up. And you will train algorithms that will be able to do that. And just as the sentence says, we'll start with a couple of boring logistics, but they're important for you to understand what's going on moving forward. And then we'll actually introduce in an almost ridiculously short amount of time natural language processing, deep learning, and the intersection of the two. So let's dive right in. My name is Richard Socher. I actually got a PhD from Stanford last year and happened to work on deep learning for natural language processing and a little bit of computer vision. I'm now the founder and CTO of MetaMind, which is a startup that also happens to do deep learning for those two application fields. We have three awesome TAs. Maybe they can wave their hands. We got Ian back there in the camera, Francois, and Peng right there. So we'll have 4 office hours at least. If the enrollment stays as high as it is, maybe we'll get a 4th one, because it'll be a lot of grading otherwise for you 3. I'm sorry we had to change the time and place. We originally had a room for only 60 people, and now we have 160 people, students enrolled, so we had to move to this. I hope it's not too bad. We'll try our best to actually record all the lectures on video and put those up. We still need to figure out if we can just put them on YouTube. We'll soon find out, hopefully this week. We will have a lot of problem sets, so basically 3 problem sets that will make you basically program these kinds of algorithms, and there will be a midterm and a final project. And in fact, the final project is something that you might want to start thinking about starting today. This is going to be an important part, and hopefully as we go over a bunch of applications, you'll see, you'll have some ideas on what you want to do. You can find our office hours and soon also office hour locations on the website. I'm sorry there will probably not be any course notes, but we will put up the slides and the videos shortly after, and if I'm on top of my things, maybe even before the lecture. So the grades, for those of you who take not a pass-fail, we basically have the 3 problem sets that count for roughly 1/2, and the midterm is 15%. In the midterm, we want to make sure you actually understand some of the very basics of the math behind what you're programming in the problem sets. The final project will be 40%. We have a milestone, and usually when you start out your project definition, you say, oh, I'm going to solve NLP, it's going to be so great and epic. And then we have the milestones, and what we often then get, I was a TA for 229, the machine learning classes, we're struggling collecting the data. And that is actually, it's a very common problem. A lot of these algorithms need a lot of data, and just storing a lot of data, it might not fit on your laptop. You might need some other machines. So we're going to give you 2 bonus points, or % of the entire class, if you have your data ready and ran a single experiment. Could be just a simple baseline if you actually have some experiments done at the time of the milestone. And then the final write-up, project, and presentation will have a poster presentation instead of the final, will be 35%. Are there any questions so far? All right. So bonus points also for exceptional poster presentations. The late policy, we're trying to not have to hear about your grandmother, so we'll give you 7 free late days. You can use them as you please, except that you can only use 3 for one problem set at a time. So after 3 days, we want to basically talk about the solutions during the office hours and want to move the class along, because the next problem set will be due 2 weeks after, and oftentimes they build on top of each other. So we want to be able to share the solution. So you can turn your problem sets in at most 3 days late. After you either exceed those or you hand it in, so once you hand it in late, it's gone, it's dead. If you exceed your 7 late days, you will lose 25% per late day after that. And it unfortunately cannot apply to the final course project, because we have to put in the grades into the system. So. Collaboration policy. Stanford recently got into the news, not so pleasantly. So please do read your code book and the honor code. Obviously, you can talk about things during your lecture and your understanding, but you have to write down your own solution, and most importantly, you have to program your own solution and not try to find some code somewhere on the internet or something like that. On the final projects, you can actually work in teams of 2 people. And maybe if you have a really ambitious project and you have a very clear setting of what's going on, we can make an exception and have 3, but ideally it'll just be 2, because otherwise it's hard to attribute who did what. All right, any questions about all the grading? Great. All right, so prerequisites. On a very high-level note, I will rather err on the side of boring some people in the beginning and make sure everybody gets the very basics of the math and the programming. So if you have taken all the prerequisites and you got A+ in all of them, and that was all pretty boring because you already kind of knew it, unfortunately, you'll be a little bored in the first handful of lectures, maybe 2. What I found TAing is it's better to err on that side, and then we can ramp up the speed as we go to more complex models. Really, once you know some of the basic building blocks of deep learning, you can very quickly put them together in interesting new ways. They're kind of Lego pieces. You just need to understand how they're put together and then build amazing stuff. So. With that being said, you'll have an easier time if you're proficient in Python. All the class assignments will be in Python. We'll use NumPy, but obviously not packages like scikit-learn, because that's the kind of stuff we want to learn how to do ourselves. So we will provide a tutorial here, actually from a previous class, 231N. And so let me ask in the room, show of hands, who would want to have a Python refresher to make sure they can hit the ground running? Raise your hand. Okay, who does not need a Python refresher? All right, well, it does seem like there are very few people who really need it. So maybe those people, in the interest of our TA's time, can just talk to some of the TAs. There are only like a handful of hands raised. And yeah, during office hours, of course. Yeah. All right, college level calculus and linear algebra will be great. So who here knows singular value decomposition? All right. This is awesome. All right, you'll have a great time on Wednesday, because we'll kind of assume that you know SVD, and we can then move to neural networks more quickly. So basic probability and statistics is also good. You don't need to know crazy Lebesgue measures or anything for deep learning, but knowing what log likelihood is and things like that will make your life a lot easier. And really, if you've have fully understood CS229 in all its gory details, you'll have a lot easier time in general conceptually moving through this class. We'll have a lot of cost functions, and basically once we write down our cost function, everything else will be kind of straightforward. You take derivatives with a bunch of matrix multiplications, and then you run some optimization algorithm like gradient descent. Any questions on the prerequisites? All right. So that was the boring part, and I'm very hopeful from the hands being raised so far that we can move somewhat quickly through the early parts of the class material. So what is natural language processing? Again, these are very, very short descriptions, and in some ways it's still a reasonably young field, so the definition is a little bit subjective, but most people I think would agree with the minimum subset here that I described, which is that natural language processing is a field at the intersection of computer science, artificial intelligence, and linguistics. You'll often find researchers working in NLP to be associated with these kinds of departments, and in some cases some universities have an AI or machine learning department, and in most cases AI is kind of part of computer science. So the main goal for NLP, or natural language processing, is for computers to understand and process natural language in order to perform tasks that are useful, and in most cases useful to us back as humans. For instance, question answering. Of course, the tricky bit here is, and the reason I put understand in quotation marks, is computers don't really understand language the way we understand language. There's a lot of linguistic knowledge, world knowledge, and the connections to thought and planning and love, life, and happiness and all that will make it very hard for a computer to fully understand and appreciate language. So and there's actually a lot of interesting stuff in the philosophy of language too, and you can spend many, many hours reading about Frege and Wittgenstein and a lot of philosophy of language, which we will not do in this class. It's very interesting, but in order to actually give you tools to do what's possible now with deep learning, we kind of have to move over that pretty quickly. So we'll basically take a very pragmatic approach and look at a lot of tasks that are very concrete and helpful to humans. And in some ways, perfect language understanding is a so-called AI complete problem, in the sense that you kind of have to solve almost all of other AI, right? I can talk about planning, I can talk about my motor control in a robot, I can talk about visual inputs, and if you really want to understand what the meaning of green is, or blue, how do you really do that without seeing the outside world, and so on. So it's a very complex problem, and in many ways we will simplify it. One thing that has been is pretty well established inside NLP are different levels of linguistic representation and skill. And so it starts with speech. Or in the case of many computers who don't actually have microphones or are not programmed to deal with speech, with raw text. Those could be pixely scans in PDF format or something. In the case of speech, we will then do phonetics or phonology, which is the subfield that deals basically with trying to understand speech and map it into a system that humans can understand and analyze. And in the case of text, we might do optical character recognition and tokenization, just finding where do words end and start. And this kind of tokenization is pretty easy for English, right? We just have spaces, but for other languages like Chinese, you might not know where a specific word starts or ends. Once you say, all right, I have at least roughly the words that I want to deal with, you can then try to understand and analyze these words. And that's the subfield of morphology. And again, for linguists, you might start cringing here because any one of those boxes could be its entire own class, right? So we're doing a very, very bird's eye view here of the field of NLP, and I'm sorry to all the real linguists in the room who might cringe now. So morphology basically tries to understand how words are constructed, if they're prefixes, so it could be unfortunately, so un would be a prefix of the overall word, unfortunately, for instance. Once you understand the words and their meaning, you in general in sort of traditional NLP, you move on to syntactic analysis, trying to understand how words are put together. So I can has cheeseburger, for instance, does not sound like a syntactically correct phrase in the English language. And syntactic or syntax basically tells you what is a reasonable syntactic phrase. How does grammar work? What is grammatical? What is ungrammatical? And so on. A lot of people in traditional NLP would assume that you need to have the morphological and syntactic understanding in order to go to the next one, but we'll actually see that in some cases deep learning can move straight into semantic interpretations or semantics, which basically deals with trying to understand the meaning of not just the single words but also how they compose into a complete sentence. And once we understand the meaning of a sentence, which is also a tricky bit, and there are lots of different definitions of what is actually the meaning of a sentence, once we understand that, we can maybe go to discourse analysis or pragmatics, which tries to deal with and tries to understand how multiple sentences form the meaning of an entire story, a novel, or a conversation between people, which can be very useful once you want to have a phone agent or something that can let you book a flight ticket and wants to needs to keep track of the things you've said already in the past. We will mostly focus on syntactic and semantic interpretations in the class, but there will be a little bit of phonetics and phonology, because speech recognition has been somewhat revolutionized by deep learning. So it's still part of NLP. A lot of people put speech into a little subsection of or separate from NLP, but clearly speech is part of language processing. So mostly we'll focus on semantic and syntactic interpretations, which are also the ones that are closer to the real tasks that we might care about. So what could those be? Are there any questions so far about the different NLP levels? Just a head scratch. All right. What are NLP applications? Basically, they range from very, very simple ones to extremely complex systems that have, dozens or hundreds or even thousands of PhDs work for multiple decades on. So some of the simple ones that we now don't even consider artificial intelligence anymore. Oftentimes we define AI as the thing we cannot yet quite do. Just like with chess, we thought, oh, once we can play chess, we have real intelligence. And then we play chess and we're like, oh, it's just some branch and bound search algorithm. It's not real AI. And we will actually observe that also in the class, where things that used to be considered amazing AI technology are now kind of, oh, I'm just talking to my phone and it's Siri, and that is not AI anymore to some people. So the simple tasks are spell checking, keyword search, which is what most search engines had worked on in the past, but now actually a lot of them are moving closer and closer to semantic analysis and harder tasks, or finding synonyms. Just setting up and learning a thesaurus is a useful task and helps people in their day-to-day lives. Next are sort of some slightly more complex problems, and many of those we'll actually tackle in the class. And you'll be able to come up with models or learn about models that can solve many of those with the same kind of model. So we could, for instance, try to extract specific types of information from literature, but also from websites. So you might want to find all the prices of a product from some free text, or you might want to find the dates and locations or people names or company names in a large document. Imagine you want to understand a novel and you want to find an algorithm that creates a social network just from reading a novel. That is something that you could do once you find all the people and how close the people's names are to each other. You can also classify text into really anything, and this is one of the very sort of simple but also powerful ideas. If you have any kind of text and any kind of label you can associate it with it, as long as people are able to assign that label consistently, you'll probably be able to train an algorithm to assign that label consistently as well. And that sounds kind of abstract and boring until you realize, oh boy, there are lots of interesting labels that you can assign to a body of text. It could be, reading levels of school texts, or it could be positive, negative sentiment of longer documents, and that might allow you to trade in an automatic algorithmic trading algorithm, which is immensely useful for some people and has some other problems. And then you come to the very, very hard tasks of machine translation, where again you kind of need to have a lot of world knowledge, linguistic knowledge, situational knowledge. You need to keep track of what has been said before, and so on. So those are very hard tasks. Similarly, spoken dialogue systems or real question answering, where you don't just do a search and then you find a website that has the answer in it, but you actually get the answer. So those are some super hard NLP applications, and we'll actually scratch a little bit on those as well. So I mentioned NLP is very useful in industry as well. So obviously we all know search, and that has modified a lot of or changed a lot of our lives in very nice ways. So we can find information very quickly. It can be written or spoken. Online advertisement is also in some ways originally a very simple task. You just find a certain keyword and you put ads right next to that. But if you actually have a better understanding and you realize, oh, there's some sentiment associated with it, and they're complaining about this, so maybe you don't want to put your ad right next to the text that says, oh, this product actually is really bad, because it's wasted money to put the ad there. You have automated, and I usually say assisted translation. If you have fully automated translation, you might get a hair salon that is called could not connect to the translator service. So that is a particularly bad example, but in other cases, oftentimes the translation is really raw. It doesn't quite get the subtleties. So for instance, if you translate "they were all pregnant" into French. Now, in French, there's a different "they" for all male and all female or mixed. And so if you now say the male, because males are unfortunately still much more common in text, so the algorithm will err on the side of using the male "they." In French, you'll say all those males were pregnant. And that doesn't work. So it's still, in many cases, just assisted translation and not fully automated. Similarly, sentiment analysis is getting better and better, also partly thanks to deep learning, but it also has its problems. So here is an interesting example from a couple of years ago where Anne Hathaway starred in a movie, and then the movie reviews came out and they were very positive. She acted really great and so on, and then immediately the stocks for the company Berkshire Hathaway rose. And so you might think, wow, it's crazy. They start doing algorithmic trading with these kinds of algorithms. And honestly, if they had used deep learning and had a little bit better sense of entity disambiguation, they may have made a lot more money. And then speech recognition is another task that can be seen as its own sort of application in industry, but really it's connected to a lot of other ones, so translation and search and so on. So let's have one very, very oversimplified slide on why natural language processing is actually hard. So I kind of alluded to this before, but there's really a huge amount of complexity in representing and learning automatically a lot of different types of knowledge. So we have linguistic knowledge. We know what grammar, what kinds of sentences give us, what kind of sentences are correct or not. We have situational knowledge. I know that there are certain things I can say in certain situations and not in others. We have a lot of world knowledge, visual knowledge that we might be referring to, and so on. So that is one of the examples. So here, for instance, let's assume we try to build an algorithm that understands who she is in this sentence right here. So the sentence is Jane hit June, and then she fell. So now, who is she? Right. Well, wait, who? June, exactly. And then, but now it's the sentences Jane hit June and then she ran. So now, it's actually almost ambiguous again, because it could be, well, you got hit and then you want to run away, or you hit somebody and then you ran away. So again, there's almost situational knowledge, but here, it's more likely to be Jane than June. And it's, in some sense, it's probabilistic. But in the first case, it's very clear that it was June. And so how do we now represent that fact that we just, for us it's very intuitive who she is depending on the verb. How do we instill that in an algorithm? And that will be one of the big questions, and we'll provide one solution in deep learning. And it's not the only one, but it's actually one that I think moving forward is going to be very powerful. So that is the first large problem. And then the second one is ambiguity. So here we have a sentence, I made her duck. So who here has an interpretation of what that could mean, rephrased? Yes?
I took her duck and I cooked it.
Exactly. I made her a duck and it tasted very, very good. Yeah.
I physically crafted a duck that was hers.
Exactly. Maybe in the end you have a wooden duck or something, so you made her, you carved one for her. Yeah.
I threw something at her and she ducked.
Exactly. Like that. And there's a fourth one that yes.
I cracked the master plan of my duck.
You what?
You make someone, like you crack the master plan of something like that.
Interesting. All right. I did not think of that one before. There's one that is actually very similar to the first one, which is, I cooked the duck for her, which could be I cooked the duck that she owned. So I actually made her duck and not, my other friend's duck. So lots of ambiguity, right? And you can probably think of even more. All right. So that leads us maybe to deep learning, though there are some problems here that I brought up that I don't know if deep learning can solve it either yet. Basically, what is deep learning? It's a subfield of machine learning, hence the prerequisite of 229 being very useful. And to really appreciate the difference between traditional machine learning and deep learning, we have to kind of look at how does traditional machine learning solve some really hard tasks. So let's take the semi-hard task of finding named entities, just identifying that like Anne Hathaway is a person and Berkshire Hathaway is a company, for instance. We can look at traditional systems that use, for instance, graphical models like conditional random fields and see how they actually solve that task. And what we observe then is that really once you dig into it and you try to improve the system or you try to really understand how it works, you find that the most important aspect of that isn't the conditional random field that gives you a sequence model on top. It's really the features that represent the decision, that represent sort of the input that we give to a machine learning algorithm. So for named entity recognition, for instance, we will look at the current word, the previous word, and the next word. Those are fairly straightforward. And then we might also look at character n-grams. So if it's duck, then it's DUC, UCK, and things like that. So character trigrams or bigrams, which just happens to be after a PhD student looked at these kinds of errors long enough, found that that is a useful feature. They ran some experiments, it helped on their development set, and so on. You might want to run a POS tagger, so a part of speech tagger that now it's a completely separate system, but oftentimes named entities are nouns. So it clearly helps to have part of speech. So now you basically ran a different machine learning system that is also a sequence tagger on the whole document and said, all right, this is a noun, this is an adjective, and so on. So, not ideal if you have to build now a pipeline system that runs one system and that first system is not modified by what you want to do afterwards. You might look at the surrounding part of speech sequences, the word shape of the actual word in question. What is word shape? It basically tells you the capitalization. Is the word all caps or just the first letter, or is it are there no capitalized letters in the word, and so on. And I could go on. So these are just a subset of all the features that in the end are in a system that now does sort of professional, state-of-the-art level named entity recognition. And so in this kind of setting, machine learning really just becomes it's reduced to just optimizing the weights to make a final prediction. And the weights are, I think in this with this kind of word shape, all caps letters, and the next word being Hathaway or something, then this is the right, this is probably this kind of named entity. So really, this is all that machine learning does in that case. It has all these weights and it tries to optimize, how important is this feature in correlation, in connection with this feature, and so on. So really, when we look at machine learning in practice, we have these two types. These two subtasks, which is first, describe your data with features that a computer can understand. A computer doesn't understand that, because she fell and she could run away, and so on. They don't have that knowledge. We have to somehow give it to them. And once we distilled all that, then we give it to a learning algorithm that just computes the weights. So really, when we talk about artificial intelligence, for a very long time in the past, it was more human intelligence of PhD students learning how to describe the features, how to describe these different tasks and different problems. And in the end, the learning algorithm was actually, just optimizing the weights. So that has, in some ways, allowed us to make progress, because it's very hard to represent everything. But it's also what deep learning is trying to overcome and in some ways deprecate, in the sense that deep learning tries to do the entire process. So you just give it raw input, it learns how to represent that input, and then it makes also a final output. So on a very high level, what does that look like? And no worries if you don't yet understand what all these kinds of figures mean. We'll really very carefully and very slowly go through those in the lecture. not this lecture, but throughout the quarter. So basically, the idea of deep learning is to do representation learning, when basically attempt to automatically learn good features or representations, like the ones I just mentioned for named entity recognition. Deep learning algorithms essentially attempt to learn multiple levels of these kinds of representations. So you start with ideally as raw of an input as possible, so just words, for instance, in the case of natural language processing, and that's kind of one of the fascinating things in the case of computer vision. A lot of the same techniques that we'll cover in this class actually also work for computer vision, and so there it would be just the raw pixels. So either pixels or words or raw speech signals, and you give those, and then you pipe them through a so-called neural network or a deep learning architecture, a model, and in the end you get some output, in this case here, the last layer. So because this lecture is recorded and there are lots of people online who will probably say, oh, but you didn't mention this person and this person's impact on the field from 20 years ago. I want to have one slide on a little bit of the history of the term. And again, it's grossly oversimplified history here. We could have an entire history on deep learning class. So basically, what we'll focus on are different kinds of neural networks. Neural networks, are only one type of deep learning. There are actually other probabilistic graphical models, but recently, and especially for natural language processing, neural networks are the kinds of models that actually work a lot better, and they're faster to train and simpler to analyze. Basically, yeah, it's become the de facto dominant model family inside the field of deep learning. You could be snarky and say, well, really, neural networks and deep learning are just clever sort of marketing terminology for what is essentially stacked logistic regression units. So if you're familiar with logistic regression, in some way we could abstract this entire class as just saying we put a lot of logistic regressions together. So on the other hand, so this is somewhat true, but at the same time, there are a lot of interesting modeling principles that come up when we try to say, oh, we're learning the features, we try to transform our inputs, we try to understand how words compose, and so on. And there are actually, in some cases, interesting connections to neuroscience, especially in the visual case that we don't cover very much. So for NLP, I will personally stay away from making any analogies to the brain. I'm not a neuroscientist. There are some people actually at Stanford too who do think that there are very interesting and important connections between deep learning and neuroscience. For us, it will be functions that we optimize, and no brain analogies from me moving forward. Also, and this is sort of just a disclaimer, we will not be taking a historical approach here. There are a lot of techniques that have been invented in the past and then have been somewhat superseded, and instead I will try to just teach you the stuff that really works well right now. And in some cases I'll mention that there's a progression of ideas here, and I will point you to the papers that you're definitely welcome to read, but we'll try to keep it as current as possible. If you're interested in the history of deep learning, there's a great paper by Jürgen Schmidhuber on deep learning and neural networks, an overview. So I'll just refer to that. All right. So why deep learning? Why do we not have a special class on graphical models and natural language processing, which there's a lot of work in that field too. Basically, the manually designed features that are often used in traditional machine learning are often overspecified, incomplete, and take a long time to design and validate, right? If you're a PhD student, you want to improve the performance on your task in order to publish a paper and improve, science and engineering. You might have to, have this idea, you look at your errors, and then you add another extra feature to it. And that's a very slow process. And in many cases, and we'll go through some examples, it'll be, you'll probably miss some things because you can't look at all the ways you could possibly negate something or all the words that are possibly positive in the world right now. On the other hand, the features that deep learning algorithms will cover in this class will be able to learn are very easy to adapt. You have a different task, just give that as an input, and all the intermediate representations and features will be learned. So basically, deep learning will provide us also a very flexible and I would say almost universal and learnable framework for representing different kinds of information or different kinds of knowledge. So I mentioned the world knowledge. There are ways we can represent a bunch of facts in neural networks. We'll have visual knowledge that we can very easily connect to also, as well as linguistic information. All right, and what's also important is we can do both unsupervised and supervised learning. So in unsupervised learning, we just give it a bunch of text and it will actually learn how to represent certain things and actually be able to extract information from just all of Wikipedia without any specific text. At the same time, I can say this is a positive sentence, find other positive sentences, and so that's also possible. A tiny historical approach to what's relevant right now is in many ways, like I said, deep learning techniques go way back, maybe starting in the 60s, and so you might ask, well, why now? Why have we not had this class 10 years ago? And so the main reason is that in 2006 these kinds of techniques actually started to work. So they were out there in theory. People had published papers on very small data sets of like 10 sentences, and they kind of had some interesting patterns, at least in the case of NLP. But really now, after 2006, and then really picking up in the last 5 years, they started to work incredibly well, and sometimes better than systems that hundreds and thousands of researchers have worked on before. The three main reasons for that is that deep learning techniques benefit a lot from having more data. And something that, if you're still familiar with 229, you will appreciate is, imagine you had a classification problem and you wanted to classify any element from this class versus elements from that class. And now, if you had a very simple model, a linear model, like logistic regression, you could only have, you'd say everything on this side is in class 1, and everything on the other side is in class 2. Now, deep learning will actually allow us to learn much more complex decision boundaries, and no worries, we'll go through all of these things here in detail, but it might actually be able to learn that this is potentially the better decision boundary. And if we have a lot of data, then this might actually, be a much better one that will, in the end, generalize better. So if you now have an example here, for instance, whereas the previous simple linear decision boundary would have not gotten that right, a deep learning model would have gotten it right. So basically, deep learning can benefit a lot more from more data. It's a very powerful model family. It'll also actually benefit a lot from faster machines and CPUs and GPUs. So your graphics cards from gaming actually has now transformed the company NVIDIA that used to build these mostly for gaming, and now they're really interested and excited about deep learning. Deep learning, in the end, will boil down to a lot of matrix multiplications, and it turns out those can be very easily parallelized. So again, a big advantage, and also moving forward, I think that there will be even more multi-core processing systems, so it'll benefit even more. And lastly, and that is kind of the most interesting part to me personally, and also the one that we'll cover most in the classes, there are actually a lot of new models, new optimization algorithms and ideas that have come up in the last couple of years. Are there any questions so far? All right. Well, I guess I'm either being very clear or everybody has a food coma. All right. So let's look at two of the breakthroughs of deep learning and how, why there was such a high impact. So the first huge breakthrough result of deep learning came for large scale and large data set speech recognition. So where traditional features had gotten you a specific word error rate in an acoustic model that basically is given some acoustic features and tries to predict a phoneme or a word from that, deep learning by somebody who wasn't traditionally an expert in speech recognition. He had not done previous work. Actually, a friend of mine, George Dahl, he was able to get a 33% reduction in error in terms of the word error rate compared to traditional human-designed features. So every time you now speak into your phone, your Android or your Microsoft phone or whatever, or your iPhone, there is a deep learning system behind that will try to understand your speech. The second huge breakthrough and we'll actually talk about the speech more in subsequent lectures. The second big breakthrough, which we won't be able to cover in this class, came in computer vision in 2012, where basically until then most of the large deep learning groups had spent most of their time on speech and computer vision. And so the big breakthrough paper here by Alex Krizhevsky in 2012 was ImageNet classification with deep convolutional neural networks. And so unlike before, you can now literally as easy as drag and drop classify different kinds of images. It's become very, very easy to use this technology. Instead of just saying this is a dog versus a house, or a bird versus a national park, like you can actually find all different kinds of birds and so on. And here are also some very interesting connections to neuroscience and sort of the visual cortex and what it does. As you learn more abstract layers in neural networks, and don't worry if you don't understand all the details here, but basically in the first layer of these kind of visual deep learning algorithms, you'll capture just very simple edges. There are lots of crooked edges or straight ones and so on, and different color features. And then as you move higher and higher in the architecture, you'll find more complex shapes. So maybe here you have some half circles and different color gradients and so on. And then as you move to the next layer, you might find specific features for wheels or certain types of fruits and so on. All right, so that was a very, very quick and oversimplified introduction to deep learning. And again, that is what we'll cover a lot more of throughout this lecture. So basically, when we say deep learning and NLP, it's sort of a long word, so we'll just refer to that in the future as a deep NLP. And basically, we're combining the ideas and goals of NLP and use representation learning and deep learning to actually solve a lot of different kinds of problems. And basically, there have been several big improvements in recent years across various different NLP levels, so speech, morphology, syntax, and semantics, as well as applications. And so in the last part of this lecture, we'll actually go through a couple of these, and that will make it a little less terse on your NLP background knowledge. But you don't really have to memorize the IPA table like you would in a phonology class. So let's look in the next couple of slides on different levels of representation in traditional linguistics and NLP versus deep learning, and then look at how those actually affect real applications. So in phonology, what linguists might come up with is different ways of categorizing different phonemes. So we have, for instance, fricatives, like that, or plosives. So they try to come up and realize all the ways that your speech apparatus can create different kinds of sounds. And in many cases, and we'll observe this in the future, deep learning actually uses some of the ideas from traditional linguistics, but only as a final output label. Internally, they will represent all these different sounds as simply vectors. So vectors as literally just a list of numbers. All right, so let's assume we're able to find phonemes in text or in speech. The next step was morphology. And so in traditional morphology, you might analyze a word like uninterested in terms of its prefix, stem, and suffix. And the sort of not quite magic, but initially it might feel like magic. For deep learning, again, every morpheme will be a vector. So just a list of numbers. And we'll actually be able to train a neural network that will combine two vectors into one vector. And really, we'll describe all this in a lot of details throughout this lecture. But you just say un is a list of numbers, fortunate is a list of numbers, and unfortunate now combines to another list of numbers. And ideally, that list of numbers will somehow capture as much information as possible. So just to give you a very rough sense of what is actually captured in these vectors, we can actually project them down using something like PCA into a lower dimensional, two-dimensional vector space. So we can actually visualize and see what's going on inside these numbers that we now just learned based on predicting something. And so what we'll observe, and I'll zoom in a second, is that we'll actually have similar linguistic structures emerging by itself from deep learning models. So all the words in this area of the projected vector space here will actually be nouns. So let's zoom into this, and what we notice afterwards is where the large areas of the vector space are just part of speech tags. Once you zoom in, you actually have semantic substructure. So the model and deep learning models that we'll cover in this class and actually start with this Wednesday will actually capture the fact that France and Germany are somewhat more similar to each other than Britain and China, for instance. And in other parts of the space, you may have a lot of verbs, and you can see auxiliary verbs, for instance, where linguists would say, oh, I think is, where, was, and are auxiliary verbs. It just learns to automatically cluster them and group them together. All right, so that is basically the way we represent morphology, and word information is just a list of numbers, a vector. Well, let's move on to the next level, which is syntax. Basically, the traditional representation of syntax, and again, I've actually personally taken like 3 different classes, or 4 actually, on syntax. So this, again, is only a very, very bird's eye view and one example picked out from all of syntactic theory. There's a lot more to all of this. But one traditional way to represent syntactic categories is just in terms of discrete phrase structures. So you might say, there's a noun phrase like the house, or a verb phrase like is red. So is a verb, red is an adjective. Together they become a verb phrase. And you may have recursive structure in here where you may have a noun phrase inside another noun phrase. So you might say the house at the end of the street is red. So now the street is a noun phrase, but off the street is a prepositional phrase where that starts with the preposition off. And so you may ask 10 linguists to come up with a tree structure, and in many cases they may actually come up with different ones. So it's tricky because we use language and it's a very fluid system, and sometimes you start making mistakes, and then if enough people make those mistakes, they actually become the de facto standard, and then so things are very fluid. Things that might have been wrong in English 100 years ago now are totally acceptable. And so yeah, discrete categories. That's the main idea. And now in deep learning, we could actually use the idea of having phrase structures, but instead of saying this is a specific noun phrase or prepositional phrase, maybe we'll just say it's a vector. And we have already vectors describing words. Now we'll train neural networks to basically take in two word vectors and produce a phrase vector. And this is kind of crazy when you think about it, right? We're now trying to represent an arbitrarily long phrase of multiple words. Maybe it's just 1 word, maybe it's 10 words, maybe it's 25 words, and just a list of numbers, right? So throughout this class, we'll have to very carefully analyze how many numbers are enough. What is actually being represented in those numbers? Are similar phrases now close to each other in the vector space or not? There's a lot of interesting questions that we can ask once we actually try to attempt this. Are there any questions? Yes?
Neural network, are you putting these word vectors into the neural network? What is it trying to predict?
That's a great question. So the question is, am I putting these word vectors into the network or not? We'll cover word vectors because they're kind of the first building block for a lot of the other subsequent models that we work on in the next 2 lectures. And true answer is that we actually often have a model that learns word vectors in an unsupervised way. And then we take them and we plug them into another system, like a sentiment analysis algorithm, for instance. Yes? Sorry, say again?
Is it a Euclidean distance?
Is it the Euclidean distance? So there will actually be a lot of different kinds of distance metrics that we can use to define similarity in vector space. It could be cosine distance, Euclidean distance, simple inner products, and so on. So we'll go a little bit into that as well. Yes?
Considering that different documents have different lengths, so when you're trying to train your neural net, is there a way to standardize the representations of the different training data? Or
is there a way to standardize different representations of the training data? So the dimension, that's a good question. So a lot of cases, a lot of experiments that we'll run, the question how many dimensions are enough will come up, and in fact in your problem sets you will have to run cross-validation experiments. You'll have to try, maybe 10 is enough for this really simple task, maybe I need 50. Maybe for a very complex large document classification task I would need more. But sometimes the longer the document is, the actually simpler the problem becomes. So if you want to understand sentiment, for instance, and you have 1,000 words to go off of, well, if you see awesome and wonderful and family and good times and so on multiple times, it'll actually become quite straightforward that it's a positive one. But if you see only a single sentence and you might say, this was not the most awesome movie, then it becomes harder because you really need to understand the one meaning of the not to get that sentence right. So it'll actually depend on the task. Great question. All right, so the last and I think most interesting representation layer, or layer of level of natural language processing is semantics. And again, semantics, very complex field. Lots of connections to the philosophy of language. You could take at least 2 very, very interesting lectures on just semantics. One way to represent semantics is lambda calculus. And I'm going to try to explain to you this expression right here. But don't worry, we'll actually not use those kinds of representations throughout the rest of the class. So no worries if you don't really understand and can follow. Basically, you assume that certain words are very carefully and human-designed functions. So you have that take as input other functions. So for instance, likes, you might say, is a function that takes as input an object entity, and then that creates another function that now requires a subject entity, and in the end produces the overall sentence representation likes MS, M for Mary and S for Sue. So that has some problems, right? One, what if somebody said liked? Now you need to have this different representation, or maybe the same for that. Also, that kind of discrete representation doesn't allow you to now capture similarity or some of the fuzziness that we have in language. So there's no connection between likes and liked, right? You would then have to say, well, those are just 2 completely separate types of words, and you're kind of stuck again with how do you make a computer understand that likes and liked and maybe enjoying to hang out with are actually roughly similar. So basically there's no notion here of similarity, and you have these discrete representations. And now you probably are starting to be able to guess it, but for deep learning, every word, every phrase from the last slide, and every single logical expression that compares different sentences will also just be a vector. And at this point, if you're a critical mind, you should start wondering if that is actually the right thing to do, right? Logic is a very discrete kind of endeavor, right? It's either true or false. This element is either in the set or it's not in the set. And so if you think about this, this will kind of blow your mind, right? Basically, we will say the sentence, all reptiles walk, and some turtles move, and everything here is a vector. Reptiles is a vector. The phrase for all reptiles is a vector. All reptiles walk is a vector. And now the comparison of all reptiles walk and some turtles move can be classified in the end as a so-called entailment relationship. If all reptiles walk, then clearly some turtles also move. So one logically follows from the other. And the crazy thing is deep learning can actually capture that. They can actually learn these kinds of logical representations. And that is something that was very unintuitive to a lot of people working in the field of NLP. Any questions so far? All right. So let's move on to some of the applications that you will be able to program throughout this class and that are exciting to work on. So the first one is sentiment analysis. And I just want to, again, sort of show you the difference between the traditional approach here and how deep learning will deal with this. Traditionally, you may have curated sentiment dictionaries that are combined with some kind of bag of words representation. So you might just say, if I want to find if this new document here is positive or negative, I will look into my list of positive words that I came up with, like awesome, wonderful, and great, and so on. And if whenever I find a word from that list that an expert created, I will say that's a positive, +1 for positive. But of course, there will be tricky sentences like badass or awesome or various other words that you might come up with now that an expert 5 years ago or 10 years ago may not have put into their list of positive words. And so that is one problem here with traditional sentiment analysis. And then a so-called bag of words representation will just say, does this word appear in the document or not? And we'll look at these more in the future, but basically that will never allow you to capture word order. And so if you say Jane loves John or John loves Jane, it would be the same if you had a bag of words representation, and that can be problematic for capturing some sentiment. Next, you might say, all right, well, just looking at positive and negative words wasn't enough. Now I want to create negation features. So whenever I see not in front of something positive, I will say it flips entirely and becomes negative, which is not quite true either. And you might think that. You might say, my intuition about sentiment analysis might tell me that's negative, but it's not quite true. So if you say, for instance, the movie was not awesome, but it was pretty good, it's still roughly on the positive side. So it's not like negation always flips the sentiment perfectly, right? And so, and at the same time, there will be slang language, ain't gonna capture everything. Basically, like the kinds of negation features that you might come up with might not be exhaustive for describing the full space. Now, here's one cool result, which is the same deep learning model, and one that we'll go over in this class, that was used for the morphology analysis, or the same model was used for the morphology analysis I just described, the syntactic analysis, the logical semantics, and now sentiment. It's the same, and in this case it's called a recursive neural network, and it's actually one that I worked on a lot during my PhD. It's the same kind of network. Allows you to solve these different tasks, allows you to represent different levels of linguistics, all in vector spaces. So it's a very, very powerful tool. And so we can kind of look at what this looks like in practice. So here's a demo from one of my old papers from 2 years ago. And here we can come up with a sentence that would, in most traditional NLP systems, would have been misclassified as positive. The sentence is, this movie doesn't care about cleverness, wit, or any other kind of intelligent humor. In a traditional system, you might say, well, it's got humor, intelligent, kind, wit, cleverness, care. How negative could it be, right? But then there's one little doesn't in front of it, and that doesn't have has a so-called scope over the entire rest of the sentence. So when you send that to a system, what it will do is basically give you this analysis. So realize intelligent humor is indeed something positive, and any other kind is, and cleverness and wit are positive. And care here, it actually makes a mistake. It thinks it's neutral, but you can see here a probability distribution, and it still realizes there's a lot of positive sentiment in here. And once it realizes it doesn't care about it, then it flips it and actually makes it negative. And again, we did not have to program, doesn't plus something positive becomes negative, right? It just learned it from a lot of examples. So we could actually say here, this movie, didn't care. And, it's still negative. Or it, does care a lot. And now it even realizes that caring a lot actually is positive all the way. So you can play around with this demo yourself, and a lot of people have, and obviously lots of people commented on it too. There's some funny things in there. It's the internet. So I tried to not censor it. So you can basically learn a lot of interesting facts from this and play around with it and see where does it break, right? You can be very, very sarcastic, or some people put in like, this movie is not good, right? And then, they're like, it should flip every time. But that's also not how humans would use that, right? If you said this was not good, nobody keeps track and like flips the sentiment, right? It's just a really strong not. So, depends. Yes?
I just wanted get some of the specs around this. How many training examples did you use? How many layers? How many?
Great question. So we will go through all of those in all their gory details, and ideally in the end you can really implement this yourself and gain an intuition. Oftentimes when you work on these projects, the very first time you implement your own deep learning algorithm, you have no idea, should I have 25 or 500 dimensions? And very quickly, after 2 or 3, hopefully programming and problem sets, you'll gain some intuition. And that can go all the way to, if you work on it for a couple of years, you get into the unfortunate situation where the very first guess that you've had is actually so good that running proper cross-validation doesn't improve it anymore. So that is actually the downside of that. So in this case, we only needed around 30 or so dimensions for representing every phrase. And every word. And this model actually is a single layer model, but it's a different type of layer, and one that we'll cover in the lecture 2. It's a tensor layer. So instead of having a standard sort of matrix multiplication, this is going a little bit into too many details. Don't worry if you don't understand that yet. But if you have a tensor, you have a much more powerful interaction. So it's a different type of neural network. Yeah.
In this case, like sentiment analysis, does the training set have to be annotated?
Yes. Yeah, so this is a good example where you really want to have a lot of annotation. So I guess to answer your other part, here you had to have 10,000 labeled sentences. And these were labeled both on the phrase level and the sentence level. All right. Let's move to the last 2 tasks of today, which are also the hardest ones and in some ways the most amazing ones. So question answering is one of the hardest tasks in NLP, and it basically in the past has required a lot of feature engineering to capture a lot of different world knowledge and other types of knowledge. So again, question answering, you might want to ask, who built the Taj Mahal, or who constructed the Eiffel Tower or something. And so what originally you would have done is, you ask, like, is the main verb a certain trigger? And if it is, then look for a certain regular expression and a certain WH word that exactly tries to, find these kinds of types of agents or a specific type of theme. And again, for deep learning, we can actually use the exact same neural network architecture that we use for morphology, syntax, logics, and sentiment to try to do question answering. And what's kind of amazing is, I'm missing the citation here. This is a paper from Mohit Ear in Maryland. The amazing thing is when we learn these kinds of models for question answering, it will actually capture that Ronald Reagan and Jimmy Carter, for instance, are quite similar kinds of entities. They're both presidents in a certain time span, or Thomas Jefferson here and George Washington. It will just learn to project these somewhere into the space. It will deal with all the gory details that we would otherwise have to think about for decades on how do we represent the fact that they're both presidents, but one sort of in an early time and was in a war of independence and so on. It'll just push that somewhere into the vector space and deal with that problem for you. Of course, that has the one big downside is you can't tell it anymore where you want it. You might say, well, I have this one specific extra fact that to me personally makes it very different. I want that number to be different. You can't do these things anymore, right? So you lose a little bit of the freedom, but at the same time, the model actually is able to store these facts in a way that gives you the best performance for the task in question. And so this specific model actually is able to compete in a Quiz Bowl trivia competition challenge. It actually beats a couple of human players. So, just to give you an idea of how crazy that is, right? You have Watson, the system that won Jeopardy against the world's expert players. That was a gigantic, very complex system that required a supercomputer to run and has access to all of Wikipedia and can look up tons of things, and it had, many, many millions of dollars being spent on it in order to get a good performance. And now one grad student was able to build a system using deep learning technology to also build a question answering system. So this is why this is such a useful skill for you to acquire. It's a very, very powerful tool. All right, so the last application for today, machine translation. Basically, again, there are lots of different levels that you can use for translation. you can try to do a direct translation from words in this language to words in that language. Just look up in a dictionary and so on. But of course, that will never give you a very good translation because it's usually an end-to-end mapping, right? One word can mean lots of different things in another language. So then, and this is again, these are progressions here over decades and hundreds of PhD students or probably even thousands in the case of machine translation that have been worked through. So you might have syntactic transfer. You look at certain phrases, and if I have a very large corpus, these are all trained on parallel corpora. So you have, here's a paragraph of, the European Parliament, paragraph description in German, here's one in English, and one in French, and one in Italian, and so on. And you might say, well, that particular phrase, not just the word, but that phrase often co-occurs with that other phrase in the other language. And then, basically you can parse and try to translate whole phrases, and then sometimes you see the whole sentence, and maybe you can try to translate the whole sentence right away. That is the next level. And then you can use the semantic level and say, well, sometimes I describe this in terms of logic. X made Y happy. And now I have this interlingua, the sort of language between the languages that abstracts away from all the complexities and subtleties of each language and has one general description, which is also very, very hard if you know like different cultures and so on. And you might say, okay, I will translate everything into this logical or very discrete semantic representation, and then I will just generate a surface form, a specific way to describe that. So what do people think is the interlingua for deep learning? Exactly, it's vectors. And so this is a very recent result from just last year. There are actually a couple of groups that are starting now to use deep learning for machine translation. But basically, the crazy result here is we could literally take word vectors, we squeeze them through a very deep, very powerful deep learning architecture, and we take the entire sentence and we just describe it in terms of one vector. And we have another neural network that just says, now translate that vector from the previous language into the other language. And it kind of works. This system is not yet as good as the system that Google has built over the last 10 years, and with many, many millions of dollars and lots of brain power. But in just 1 year, one group of deep learning experts could build a system that's actually very competitive. And if you can do that so quickly, it's only a matter of time, I think, but again, I'm optimistic and slightly biased, that it will outperform human systems. Because unlike for sentiment, it is basically impossible to describe all the features for machine translation by hand. Right? You can have no set of people could do that. It changes over time. It's incredibly complex. We had a question there?
So could it actually be transitional so that if I translate from English to German, like by just having training examples, English, French, and French, German?
You can do that. In fact, some people, you could do that with any system, and it just gets worse and worse. And at some point, it's so ridiculous. I think there's a video on YouTube where people translate a song lyrics like 5 times through a translation system, and it just comes out pretty much garbage. But it's possible. All right, so this was today's first lecture, very high level, very bird's eye view. In the next lecture, we'll actually look at the first and most important representation that all these different models start from, which is word vectors. And we'll see that these models capture lots of interesting facts about them. Thank you.